Hi, I'm Mark Russinovich, CTO of Azure, and today I'm going to talk to you about the COCO framework, the foundation of blockchain for business. Now, here at Azure, we've been working on blockchain for a while, and we've been making exciting progress. For example, we've allowed enterprises or enabled enterprises to deploy the blockchain network of their choice on top of Azure with just a few clicks and the use of Azure Resource Manager templates. We've also integrated blockchain networks with Azure infrastructure and middleware, such as Azure Key Vault and Azure Active Directory. And we're building groundbreaking new applications and business models on top of this support. Now, for commercial enterprises' use of blockchain, there's a number of limitations that sometimes get in the way of the full potential of a distributed ledger. One of them is that many blockchain networks suffer from scalability problems, including throughput and latency, where enterprise networks or enterprises are used to the throughput and latency they achieve from centralized databases and can't achieve that on blockchain networks that rely on something like proof of work and cryptographic means to commit transactions, resulting in transaction commit times of tens of seconds and throughputs that can be as low as 20 transactions per second. Another problem with many blockchain networks is they lack any confidentiality model. In other words, any enterprise member of a consortium that has a node is able to see the full contents of the blockchain. And then finally, in most enterprise networks today, governance is left as an out-of-band process, where the members must agree on changes to the blockchain network, rather than have a blockchain governance be built right into the network itself. COCO addresses all of these limitations through a combination of advanced cryptography, novel consensus mechanisms, and the use of secure hardware, such as Intel SGX. It's important to keep in mind that COCO is not a ledger itself. It's a framework, and it enables arbitrary ledgers to integrate with it and then achieve the benefits that come with the COCO framework, specifically scalability, confidentiality, and built-in governance that enterprises need to achieve real business results. The prototype that we've created here, that I'm going to be showing you, of the COCO framework, relies on the Raft consensus protocol, uses secure point-to-point communications using TLS, and is built on top of Intel SGX enclaves. It's got a configurable constitution that governs membership such that the members can vote to add new members to the consortium and also vote to eject members from the consortium. And the distributed ledger we've integrated with COCO framework in the prototype is the Ethereum network. But like I mentioned, arbitrary blockchain networks and distributed ledgers can be integrated with COCO to achieve its benefits. What I'm going to show you is a couple of demos. One of them that will demonstrate the scalability that COCO framework provides in terms of throughput and latency, and another one, a supply chain scenario using the Mogic supply chain software, where we've got multiple retailers and suppliers that take advantage of COCO's framework's confidentiality to prevent suppliers from seeing each other's purchase orders or inventory. So what I'm going to show you is COCO framework's ability to provide confidentiality in an example consortium scenario. In this one, we're going to have a supply chain where we've got multiple suppliers and multiple retailers. Now, to simplify it, I just have 2 retailers and 2 suppliers, and what we've implemented on COCO is a confidentiality model such that one supplier shouldn't be able to see another supplier's orders or inventory, and retailers shouldn't be able to see each other's orders either. I've got a dashboard here that is seen by one of the retailers, retailer 2, Trey Research, and what they want to do is open a purchase order against one of the suppliers. The first step they'll take is to go to the purchase orders page and then click New Order. At this point, there's some default information filled in. We're going to select an approver. We've got the admin as the approver, and now we want to add some products to order. In this case, I'm just going to order one product. We've got a universal product code in our system. I'll pick the second one here, pick a number of items, and then a subtotal that we're going to pay for that item. Let me save that purchase order and then create the order. In this system, we're using Ethereum, and each of these purchase orders is represented with a smart contract. What I've just done when I created the order is submit the smart contract to the Ethereum network on top of the COCO framework. Now, because I haven't specified any suppliers or any retailers as having access to this purchase order, only retailer 2 has access by default. And we can go verify that by taking a look at the purchase order here that was just created by selecting it and copying it, and then going to the dashboards of the other retailers. Here I have retailer 1 dashboard. If I go to the blockchain view, go to smart contracts, again, each of these purchase orders is represented with a smart contract, and enter that new purchase order. Sure enough, no results are found. If I go similarly over to retailer 2 though, and go to smart contracts, enter the purchase order, and do a search, I'm able to see it. I've also got the dashboards for the 2 suppliers here. Here's supplier 1, and when supplier 1 takes a look at it, they're also not able to find the purchase order because it hasn't yet been assigned to either of the 2 suppliers I have here in this example. Here's the other supplier. If I go to smart contracts, enter the purchase order, again, no results. So at this point, the smart contract's authorized only for retailer 2. And now what retailer 2 needs to do is assign that smart contract to one of the suppliers. So by clicking on it, I can then pick supplier 1 or supplier 2. Let's go pick one here, assign a role. And what I've just done is updated the smart contract and then authorized one of the suppliers, the one that I want to issue the purchase order against, to see that smart contract so that they can fulfill the order. If I go back into the dashboards here for the 2 suppliers, here I've got Contoso, and the purchase order was issued to Contoso. So when I do a search again, I'm able to see that purchase order. Yet the other supplier is still unable to see it. And so with Cocoa Framework, we were able to very easily take a smart contract, add a few functions that perform authorization, and implement a confidentiality model. It's important to note that Cocoa Framework supports basically a lift and shift of Ethereum smart contracts, and we've, in this prototype, not modified Ethereum in any way, not the EVM, not the Solidity language, but rather just implemented a standard function interface for authorization that Cocoa can call into to check to see who has access to a smart contract. So it's very simple to bring smart contracts, and even ones that don't need confidentiality will simply run as is on top of the Ethereum network running on the Cocoa Framework. We've added some confidentiality to these examples, but it was a fairly simple amount of work to implement that confidentiality model. And so Cocoa Framework provides this confidentiality model as well as others, arbitrary in nature. We could have made it so that both suppliers could have seen it or both retailers could have seen this purchase order. But this is just one example of the richness of confidentiality that Cocoa Framework can provide. So let's see how the Cocoa Framework can improve the scalability of distributed ledgers. Now for this comparison I've got here, we've got the stock Ethereum network and Ethereum integrated with the Cocoa Framework running as multi-node systems, multi-node networks, on the same hardware. I'm going to press the compare button and then describe what we're about to see. What we've done is taken 2,000 transactions off the public Ethereum network and submitted it to both of these implementations. We're going to look at the throughput as well as the latency at which they commit those transactions. Now, a few comments about the way that we're measuring this. First, on the Cocoa side, we're submitting in batches of 100 transactions. And this is one of the trade-offs you can make with Cocoa, is the size of the batch versus the kind of latency that you're looking for. The larger the batch size, the higher throughput you're going to get, but the latency is going to suffer. And we've picked something kind of in the middle here, and you can see that we're achieving about 1,600 transactions per second throughput, with a latency that is about 150 milliseconds. Now on the Ethereum network, what we're able to see here is that we're achieving a transaction throughput which is pretty close to what we'll see in the public Ethereum network of anywhere between 15 to 25 transactions per second. And we're seeing latencies up in the tens of thousands of milliseconds. And so what this demonstrates is that with integration of an existing distributed ledger, in this case Ethereum, on top of the Cocoa Framework, we're able to take advantage of the Cocoa Framework's distributed consensus algorithm, which relies on a trusted execution environment. In this case, we've got the prototype running on top of SGX to commit transactions very quickly and very securely. And we're able to achieve performance improvements of roughly 2 orders of magnitude over what's achievable on stock distributed ledgers.